Today we're going to be talking about energy, principal quantum number, orbitals, and electron configurations. Basically, you got to pull up what you remember from the last exam, that of figuring out how many protons, how many neutrons, and especially how many electrons are given in any given element on the periodic table based on its position and its atomic number on the periodic table. So we're going to pull from some of that information and go a little bit further and look at these electrons and see, okay, how do we know how much energy they have? How do we know its position? How do we know what's going on with the atom? And so we're going to look at those concepts today. So to begin with, the Bohr model of the atom is kind of the model that we might have looked at from so far. Kind of the idea is that you've got a nucleus in the center, and then electrons orbit around that nucleus. Alright, so think about all of your history of the atom and all the different scientists that contributed to this theory and to this thought. No longer are electrons just randomly dispersed throughout, like, you know, in a plum pudding model or that kind of thing, but instead they've got real orbits. We're going to go even further in that. So first off, before we go further, look first at how I have them labeled. N equals 1, N equals 2, 3, 4, 5. As you get further away from the nucleus, that N number gets higher. Okay? Additionally, what's going to happen is as you get further away from the nucleus, the electron's going to have a whole lot more energy. Now why, you might say? Alright, well, let's think about it this way. Let's think about it in terms of like a ladder. In order to climb up a ladder, does it take more energy just to climb to the first rung and go, I made it? Or what if you have to climb all the way to the 6th rung? Okay, or all the way on the roof of your house? Okay, the farther up you get on that ladder, the more energy it took you to get there. Additionally, notice that there's all of these different rungs. That's how ladders are made. If they didn't have rungs, you couldn't climb it. You can't just, you know, if you got the two sides of a ladder, you can't just reach for it. If there were no rung there, your hand would just drop down to the next thing it found. And so you can only climb where there are rungs present. You can't rest your foot on something unless it's there. That is exactly how orbitals exist. The idea is it takes a lot more energy to remain far away from the nucleus. Because remember, what type of charge does the nucleus have? Positive. And what charge does an electron have? Negative. So they're going to want to be close to each other. In order to exist further away from the positively charged nucleus, that electron has to have a lot more energy. So that's why N, which is our principal quantum number, correlates with energy. The more energetic it is, the higher its principal quantum number. It's like that electron climbed to the very tip top of the ladder. Additionally, these differences in between each rung, what they're called is they're discrete. Discrete means that there's a specified amount of space between each rung. The orbitals are not spaced like a ladder, where hopefully each rung is evenly spaced. Instead, as you notice up to N equals 5, N equals 6, they're getting closer together. But the idea still exists that you can't just come here in the middle and say, oh, this is N equals 1.5. No, that doesn't exist. And so what you've got is you've got specific placement of the orbitals because you have specific amounts of energy. You can't just give it partial amounts of energy. You have to give it a total amount in order to get it to exist from 1 or 2 or so on. So if I were to ask you what is the principal quantum number, you could tell me that it's N and it correlates with energy. Whereas you increase your principal quantum number, you're increasing the amount of energy the electron has, and you're increasing the distance it exists from the nucleus. Alright, so why does this matter? Well, why it matters is let's say you've got an atom, and there's some form of radiation that comes in and collides with that atom. That's this energy absorption part. So if you're given an atom a bunch of energy, what is that atom going to do with it? Well, what's pretty neat is sometimes you have an electron, say where it's existing right here in the N equal 1 principal quantum number, and if it absorbs that energy, what can actually happen is it gets excited. It said, wow, I didn't have a lot of energy, but now I can climb that ladder, and now I'm going to be so excited, I'm going to climb all the way up here to N equals 3. Okay, that's great. But it's not going to keep that energy forever. It's going to want to relax back down. It's just like you. If you climb to the top of your roof, eventually you're going to want to come down to eat, to relax, you know. Electrons are the same way. They want to come back to what's called their ground state, which is their original position here, n equals 1. So in order to do that, it's then got to relax back down. And so that's what's shown here with this relaxation. It could relax down to n equals 2, or not shown here, but it could also relax all the way back down to its ground state, n equal 1. So when it does that, it's got to give off energy in order to relax. And so when it gives off energy, it's going to emit that light, and that's when you see things like fluoresce or glow or just simply a light bulb. What's going on there is the electrons were excited via some source. So for instance, in our homes, you make your light bulb be excited by giving them electricity. That's that energy absorption part. Then that filament gets really hot and it glows, and all the electrons within that filament can then relax down to their ground state, and then that they give off light, which is what we see and what allows us no longer to have to use candles all the time. So that's the idea of excitation and relaxation. And the reason this works so well is because we have this model that tells us, electrons excite, that means they absorbed energy, go to a higher level, and they relax down and release that energy. So if I were to ask you, which one would release? Over here we've got a little waveform drawn, and we'll talk more about that waveform here in a second. If I were to ask you which one would release more energy, an electron that was excited up to say n equals 5, that then jumped down to n equals 2, or something that was excited up to n equals 5, that then relaxed down to n equals 3. Which one of those should release more energy? The first one, from 5 to 2. Why is that? Okay, well, let me ask you the question. To go from a ladder and jump let's say you jumped from the 5th rung of the ladder all the way to the ground, thud. Or let's say you jumped off from the 1st rung and hit the ground, softer thud. You had less potential energy at that lower rung than you did the higher energy, and so that's less force that you'd be hitting the ground with. It's the same idea. There's a smaller distance between 5 and 3 than there is in 5 and 2, and so there's less energy in this release than there is with the 5 to 2 release. So all of these different relaxations is actually what gives us our color. So let's talk about how that's possible. Alright, so in this example, we have a hydrogen lamp that's going to be turned on. The electrons are excited, and then they're going to relax. And when they relax, they emit that light. Then if you shine them through that prism, you know what's kind of neat? You don't see that beautiful rainbow like you see for white light. Instead, you only see approximately about 4 lines. 1, 2, 3, 4 that you can see here. Now, why is that? Well, the reason behind it is what we just discussed, with the idea is that there are only specific energy levels that exist around an atom. Each one is discrete, as we said before. With white light, there's a whole bunch of possible transitions. But with hydrogen, what do we know about hydrogen? Okay, it's got what? 1 proton in the nucleus. How many electrons does it have? That's right, 1. So if we were to draw its planetary model here, we could draw a whole bunch of more orbitals around here. Whee! And the idea is for every different transition, so it could go up to n equal 2 and then go back down to n equal 1. It could come up here to n equal 2, n equal 3, and then back down to 1. It could come up here to n equals 4, back down to 1. And so the idea here is every 4 of these lines are a different transition. So either 2 to 1, 3 to 1, 4 to 1, or it could even be a 3 to 2 transition or a 4 to 2 transition. But the idea is there's only 4 of them in our visible spectrum, meaning the other ones produce so much energy that the waveform that's produced is going to have a lot more energy than what we can see with our eye. Okay, helium similar. So if you can see 1, 2, 3, 4, 5, and neon's got a lot more. And so why does neon have so many more? Well, think about it. Neon, it's got a bunch more electrons than hydrogen and a lot more than helium. And so with the increase in number of electrons, you have a lot more of these transitions that can happen. Whereas white light, it's infinite. Okay, and the reason for that being is because there's a whole bunch of transitions that are possible just simply due to the nature of white light. White light covers the entire range. And so this is actually how they figured out that these principal quantum numbers must be like rungs of a ladder. They must exist in steps. They can't have like half steps, they must have whole steps. And so it was hydrogen's light spectrum that gave them this idea. Alright, so let's look at a couple of vocabs. First of all, emit, that's what we've been talking about, the idea of giving off light. Whereas absorb is the opposite. That's where you take in the energy. So let me ask you this question. If something is green, what colors does it absorb? Does it absorb green, or does it absorb everything but green? It absorbs everything but green, because the green is what's being reflected, and that's what we see. Alright, so that's the kind of the difference between emission, emittance, and absorption. Alright, so how does that relate to this waveform that we talked about? Alright, so this waveform, there's a couple different things you need to know and understand terminology-wise. We have wavelength. We're shown here, wavelength is this symbol here, okay, our lambda. And lambda is the distance between either one trough and another trough, or one crest and another crest, the distance here. They're the same distance, and so that's the definition of a wavelength, is the difference between a crest and a crest, or a trough and a trough. It's the space between them. And so that's why you're given units of normally meters or centimeters. Now frequency is the number of wavelengths that pass through a point per second. So meaning, if this is my point, how many of these wavelengths are going to pass through this point per second? And so that's why you get the units of a hertz, which is 1 per second. So if something has a 1 hertz unit, that means you had one waveform pass through every single second. What about light, or our 60 hertz, because we've got 60 hertz is what our electricity flows through in our homes. So 60 hertz, what does that mean? What that literally means is you have 60 of these waves pass through every single second. Light travels extremely fast, 3 times 10 to the 8 meters per second. So that's the distance that it travels every single second, if you can imagine that. That's why light is so fast. Okay, so those are kind of the main terminology. So when we're talking about that, that's why we want to be concerned about this distance here, and then also, does it have a really high frequency? Or does it have a really low frequency? Alright, let's look further at this then. Alright, so which of these would you consider to have a high frequency? Which ones of these would you consider to have a high wavelength? I hope you answered like this. The top one has a high frequency, but a low wavelength because the distance from here to here is small. But a lot of waves would pass through for any 1 second. Whereas this is the opposite. It's a higher wavelength compared to the small wavelength up here. But then for any point per second, it's going to pass through a lot slower, and so it's going to have a low frequency in comparison. Alright, so then if we think about the full white light spectrum, what that means is it contains a whole bunch of different waveforms, and that's why we see all the different colors. And so with white light, what that means is it's got some low frequency, it's got some middle ones, it's got some really fast ones. Okay, so white light is basically producing wavelengths of pretty much every color, every frequency, and every wavelength that we can see. So how they're related to each other is the big question. So what we've got here is we've got our high energy on this side. Notice to the frequency. It's really, really energetic, really high frequency. And so that's why as you go this direction, you're increasing in frequency. But what happens to our wavelength as we increase? Our wavelength decreases. So that's why wavelength increases as you go this direction. So if you have a high frequency, that means you have a low wavelength, but it also means you have a high energy. That relationship is very important. Additionally, all of these high energy, what do we see over here? We see gamma rays, X-rays, ultraviolet radiation. These are the things that do damage. Gamma rays, X-rays, you can only have so much of that before you start to die. Notice you can't just go in and get an X-ray every single day. That would be bad. Ultraviolet radiation, what can that cause? Cancer. So these are the really high energy things. That's the things that destroy cells, destroy interactions within our body that are very important. Here in the visible range now, these are also high energy, at least compared to infrared, microwave, and radio. Radio being the weakest, that's why we're able to broadcast all of our music on radio waves. It's a really low frequency, a really low energy, and so it's not going to cause us damage. So we can have a whole bunch of radio waves going on in the atmosphere. Okay, so then our visible is right here in this middle region. So 750 nanometers to 400 nanometers. So if you think about that, that means that this violet color has the highest energy of the colors, and the red has the lowest energy. It also has the highest wavelength of all of them. That's why 750 is over here, and 400 is over here. Down here at the bottom, what you see is the equations that help govern it. And so kind of this one right here in the middle is kind of the important one, where c is your speed of light, and so that's what's defined right here, 2.998 times 10 to the 8th meters per second, or on the previous slide you saw it defined as 3.0 times 10 to the 8th meters per second. Either is acceptable. One's just more accurate. This one's more accurate. So if you have the speed of light, then if we look at v, which is our frequency, so frequency is our nu. And then what did this lambda stand for again? Wavelength. So these are what's called inversely proportional. So as you increase one, you decrease the other. So increase your frequency, you're going to decrease your wavelength. That's basically what that's saying. And then for a photon, that's this equation right here, where if you're asked how much energy does a photon have, a photon has h, which is Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. And if you got Planck's constant times your frequency, that'll tell you your energy of a photon. Or if you put Planck's constant times the speed of light divided by the wavelength, you'll also have your energy of your photon. And so these are just kind of the equations that can help you figure out, if you know the frequency, you can figure out the wavelength, and vice versa. So anytime you know one variable, you can always figure out the other. Additionally, I like to kind of think about this conceptually, because I really do think that just understanding the idea that as you increase frequency, you're decreasing your wavelength, and you're also increasing your energy. I think that's very important. So then I try and think about, okay, well, how do I remember that gamma, X-ray, and ultraviolet are higher energy? Okay, well, let's just think about like X-Men. High energy, you know, what can you do with X-rays? What can you do with gamma rays? They can penetrate, you know, your skin, your bones, okay, extremely high energy. Whereas the lower wave ones, radio waves, most prevalent, lowest energy. Then microwaves, they cook our food, and infrared's a little bigger than that. Okay, so think about like infrared, that's what you might have on your remote control. And then visible's in the middle. So then how do I remember Roy G. Biv? Red, orange, yellow, green, blue, indigo, violet. How do I remember that violet has the most energy and red is the least energetic? I like looking at this comic strip. So this is Foxtrot. He's going to the store and he asks the cashier, "Do you sell ultraviolet bowl?" And the guy says, "Excuse me? What about regular violet bowl?" No. Blue bowl? No. Green bowl, yellow bowl, orange bowl? No, no, no. Rats. Okay, I'll take a red bowl. And then he says, "I was hoping for something with a little higher energy." And then his friend says, "At least it is an infrared bowl." So I kind of use this comic strip and I kind of remember myself, okay, Red Bull, that's the lowest energy one. It's kind of ironic that Red Bull's called Red Bull. Shouldn't it be called Violet Bull? Yep, it sure should be. And then at least it's not Infrared Bull, because that tells you that Infrared Bull is even worse than Red Bull. It's even lower energy than Red Bull. So if you bought an Infrared Bull from the store, you'd expect to have a very low dose of caffeine and sugar. Kind of even funnier of ironies, this last couple of years, I don't know when, but I know my student this semester bought me one of these Red Bulls. So this comic strip was from 2004, and just this past semester, he brought me the blue edition of Red Bull and the red edition of Red Bull. So I kind of thought that was funny, that Red Bull was like, I don't know if they knew about energy levels, and they thought that they could market a blue bowl as a more energetic variation of their classic silver, but for whatever reason, this Red Bull, that would be low energy, and your Blue Bull would be a higher energy. So if that helps you, great. I don't think they actually had a variation of sugar and caffeine content, but they should have. That would have been really neat. Okay, so kind of that's your thought, is red, lowest energy, infrared, lower, microwave, lower, radio, even lower, all the way to blue, then indigo, violet. Those would be your more energetic colors, and then it keeps going, ultraviolet, X-ray, gamma, and so that's kind of the order that you've got for your energy correlating with your waveforms. Now remember, all of that then correlates with your planetary model, the idea that these electrons are absorbing energy, getting excited, going up the ladder to a higher energy level, and then whenever they relax back down, they emit light that has a specific waveform, and that specific waveform produces a color. So that means that if you produce something that's red, so all of these red colors right here, those are your lower energy transitions. So that might be an electron that's gone from an n equals 2 to an n equals 1. Whereas if you have something like blue or violet, those are your higher energy transitions. So that would be like n equals 3 all the way down to n equals 1, or n equals 4 to n equals 2. Okay, whatever it is, it's all comparative. So the idea here is you've got a transition that correlates and produces an energetic waveform, and that waveform can be seen by either our eye if it's in the visible spectrum, or if it's not in the visible spectrum, we have fancy instruments that can detect it, but that's not for today's lecture. Alright, so we've kind of already considered the conceptual model of an atom, the idea that the model, there are protons and there are neutrons, and those exist within the nucleus. The proton's positive, the neutron is neutral, the electron's negatively charged and exist outside of the nucleus. Then we have the planetary model, the idea that electrons orbit around the nucleus. It is limited ability to make predictions. The other bad part about it is it only shows the S or the P subshells. Now you may be saying, well, what in the world is an S or a P subshell? We'll get there. Okay, but note that the planetary model only shows those two subshells. After this lecture, come back, look at the slide again, and see if it makes sense to you at this point. Alright, so while these models are helpful, they're still limited. And so we got to use them, but we got to keep going. We can't just stop there. Alright, so let's talk more about this idea of energy. So we already said that we've got our energy. The further you are away from the nucleus, the more energy you have. Within that, then, we have these what's called subshells, S, P, and D. These subshells each have a specific shape. So the S subshell is going to be spherical. The P subshell is going to be what I call a dumbbell. Kind of looks like you're lifting weights. And then the D is going to be more of a clover or a flower. Some people call it a flower, some people call it a clover. But no, both correspond to that. And what this means is, like we said before, as you get further away from the nucleus, you get more energy. Well, additionally, within each individual principal quantum number, each shell, as we'll call it, there exists these subshells, this S, the P, and the D, which means you're going to have a shape that's holding in your electrons, and your electrons are flowing freely within these shapes. And each of these shapes then is called an orbital. additionally, those are all orbitals. So your S, your P, and your D are subshells, whereas every different shape that you saw was an orbital. So this is a slide that I hope kind of breaks down what I just said word for word. So a shell, that refers to your principal quantum number. So aka how far it is from the nucleus, how much energy is associated with the electron. Then the subshell, it's a small classification of the shell. So think about this S, the P, and the D, and the F existing on top of or within every single N. So if you've got an energy level of N, you also have a subshell within N. And then further subclassification of subshells are called orbitals. And every orbital can only hold 2 electrons. So the whole idea behind this kind of classification system is figuring out where all of our electrons are. Okay, so every orbital can hold 2 electrons. Now note, the S subshell has 1 orbital, the P has 3 orbitals, the D has 5 orbitals, and the F, which I haven't shown you, has 7 orbitals. We're really, for this class, only going to focus on S, P, and D. F can be used for like general chemistry if you go on and take that. But just note, it's the same idea, same concepts, it just has more possible shapes and a lot more energy. Alright, so let's look back at this slide again. So remember, what did I call S, P, and D? Those were our subshells. And what did I call each of these shapes? Orbitals. So, I want to ask 2 questions. 1, how many orbitals are in S? So how many orbitals do I have? I have 1 orbital drawn in S. What about P? I have 1 orbital, 2 orbital, 3 orbitals. Notice their axis is oriented a different direction, but you have 3 different orbitals, so there are 3 orbitals in P. Okay, and then in D, how many orbitals do I have in D? 1 orbital, 2 orbital, 3 orbitals, 4 orbitals, 5 orbitals. So I have 5 orbitals in D. The next question I want to ask is, how many electrons are in each subshell? So what I mean by that, on the previous slide, what I said was you can have 2 electrons maximally in any orbital. So each of the things we just circled are orbitals. What that means is in any orbital like this one, you can have 2 electrons exist in it. So in S, how many orbitals, how many electrons can I have? Well, there's only 1 orbital, and every orbital can only hold 2. So in S, you can have 2 electrons. What about in P? Well, I can have 2 electrons in this orbital, 2 electrons in this orbital, and 2 electrons in this orbital. So I can have a total of 6 electrons. And then in D, I can have 2 in this orbital, 2 in this orbital, 2 in this orbital, 2 in this one, and 2 in this one. So in D, I can have a total of, 10 electrons. And that's kind of why we're doing this, is we're trying to figure out where our electrons are, because that's going to tell us about how energetic they are. Meaning, S compared to P, which one looks more complicated? The P does. P is always more energetic than S. Guess what? D is always more energetic than P, and definitely more energetic than S. So once again, it's going to tell you a little bit more about energy levels. So this whole idea of figuring out orbital diagrams and electron diagrams and figuring out where electrons exist, it all goes back to this basic vocab of what is a shell, what is a subshell, what's an orbital, and how many electrons can go in every single orbital. Okay. Alright, one last rule that we have to know before we can figure out the orbital diagrams for every element, and that is Pauli's exclusion principle, which is basically no 2 electrons can exist in the same place going in the same direction. Meaning, you know how we drew 2 electrons in every one of these orbitals? Those 2 electrons might be in the same place, but they can't go the same direction or else bad things would happen. Okay, basic idea. So if they're in the same shell, the same subshell within that shell, and the same orbital within a subshell, they must move in different directions. And so that's how we end up with different electron spins. So electron might either be going clockwise, or the electron might be going counterclockwise. And so this prevents them from being the exact same electron simply by having different spins. Alright, so for the rest of this lecture, we're going to focus on two things. That we can figure out how and where an electron resides by looking at either orbital diagrams or electron configurations. So, orbital diagrams, we're going to start with that. They demonstrate where each electron resides by placing each electron in a box or in a line. Each box or line represents an orbital, so that can be either the spherical shape, the dumbbell shape, or the clover shape. And each arrow, we're going to draw arrows within each box or each line, and each arrow represents an electron. Additionally, the upspin versus the downspin on them will represent either counterclockwise or clockwise. So note that each box represents an arrow, and each arrow represents an electron. And so these are called orbital diagrams. And then electron configurations we'll cover next. They demonstrate where each electron resides by using coefficients and superscripts to denote energy level and subshell. And you can either write them in longhand or in shorthand. So let's first look at orbital diagrams. These are orbital diagrams. So the idea here is that it combines all of the main concepts we've talked about so far. And that being, first, our energy increases as you get further away from the nucleus. So notice, principal quantum number of 1, 2, 3, 4. What's happening as my number gets bigger? It's getting higher and higher in energy. That happens for S, it happens for P, it happens for D, and it happens for F. All of these increase in energy as that number in front of the orbital, or in front of the subshell, increases. There's a couple other things to notice here. What do you notice about, for instance, the position of every n equals 5? Meaning we have a 5s, a 5p, a 5d, and a 5f. Which one is most energetic? The 5f. Then the 5d, then the 5p, then the 5s. And it always works this way, where the f is always greater than the d, and always greater than the p, always greater than the s, within a principal quantum number. Meaning, where the coefficient in front of the subshell is the same number. Okay, so our 4s, see how they get higher as it goes from S, P, D to F. Okay. Additionally, each of these boxes, what do we say about the number of orbitals that exist within S? There is only one. How many orbitals exist within a P? 3. How many orbitals exist within a D? 5. And how many orbitals exist within an F? 7. Then you can ask the question, electrons. How many electrons can go in every single orbital? 2. And so that's why you see your 2 orbitals drawn, 2 electrons drawn in every single box. Okay? So these are your orbital diagrams where you've got boxes, or you could represent each box with a line. And the idea is you want to fill these lines based on energy levels. Alright, this is Aufbau's principle. The idea that as electrons are added to a nucleus, the new electron chooses the orbital that will produce the most stable conditions for the atom. Meaning, you always fill 1 before you fill 2. You always fill your 2s before your 2p. You always fill your 3s before your 3p. And it goes in this order, this kind of staircase type order. This is the order you fill it in. Notice that it doesn't go 3s, 3p, 3d, 4s, 4p, 4d, 4f. Instead, goes based on energy, and the idea would be that 4d has more energy than 5s but less energy than 5p. And so Aufbau's principle lets you fill the lowest energy level first before going on to the next one. So I kind of recommend just learning how to draw this diagram and simply be able to fill it in. So the idea is you go 1s, 2s, 2p, 3s, 3p, 4s, 3D, 4P, 5S, 4D, 5P, 6S, and you always fill it in that exact same order. So what do I mean by this, fill it in the same order? All right, let's do an example. Okay, this is a box, and you're welcome just to kind of print it off or make copies of it. That's basically the boxes are drawn in the same order for the diagram. So let's pick out an element. Let's do fluorine, for instance. Okay, with fluorine, how many electrons do we have? 9. So we want to fill in these boxes based upon our 9 electrons. So you always fill each subshell before going on to the next subshell. So with 9 electrons for fluorine, we have 1, 2 electrons. We filled all of 1s before going on to 2s. 3, 4. Okay, we've gotten 4 electrons filled now. Now, within 2p, the rule is you always fill all of the electrons going in one direction first before coming back and filling in the opposite arrows, the electrons going the other direction. So I have filled in 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's the orbital diagram for fluorine. Notice you could excite electrons up into the higher energy levels, but that would take more energy. Since electrons are lazy, they fill the lowest energy orbitals first before trying to fill higher energy ones. Okay, so that is fluorine. Let's pick another one. Let's pick a higher level one. How about calcium? Calcium has 20 electrons. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And there is the orbital diagram for calcium. Alright, I think I have room to do one more, so let's pick an even higher one. Tellurium. Tellurium. How many electrons? 52 electrons. Let's do this. Let's go back to one we haven't used filled in yet. 52 electrons. It's going to take a while, but we can do it. Alright, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52. Whew. And that is telluriums. Okay. Now notice, we're going to switch here in a second to go from electron configurations to, from orbital configurations, which we just drew, to electron configurations. So notice, when we're doing that, we're going to take each of the electrons that we just drew and put it as a superscript on the subshell. So meaning 1s, how many electrons are there? 2. 2s, how many electrons are there? 2. 2p, how many are there? 6. And we can fill these in so that we know how many electrons are on each and every section. Okay, let's do another example of that. Alright, so for instance, let's choose an easier one. Let's do chlorine. Chlorine has 17 electrons. So if we fill it in, same idea as the box method. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Alright, so we've now filled in our orbital configurations. our orbital diagrams. We need to turn this into electron configurations. So the same idea as previous. We want to write down as a superscript how many electrons are in every single subshell. So 1s, and there were 2 electrons there. Then next is 2s, and there were 2 electrons in this one. Next one is 2p. I have 2 electrons in every single orbital, so it makes 2p6. Then next is 3s, 2. Next is 3p. How many are there? 1, 2, 3, 4, 5. And this is the electron configuration, whereas that part is the orbital configuration. The idea here is that electron configurations let you more quickly write out the orbital configurations. Orbital configurations just seems to take up a lot more space, but sometimes it's nice to be able to see it. Now once again, the whole reason we're doing this is so that we can see where our electrons reside. More importantly, here in a little bit, we'll talk about how we can look at orbital configurations to see our valence electrons very quickly. Okay? Alright, so here's some example electron configurations. You see anything in particular that's interesting about all of these? I picked all of these not at random. What is similar about all of them? 1s1, 2s1, they all end in s1. So where do you think they exist on the periodic table? Oops. That's right, the first row. 1s1, 1s2, 2s2, 1s1, 2s1, 3s1, 4s1. You can use these electron configurations to help explain the valence electrons of your element. Meaning, everything in row 1, guess what it ends in? S1. Everything in your second, what do you expect it to end in? S2. Everything over here? S2P1. S2P2. S2P3. S2P4. S2P5 and S2P6. You could go back through and prove this to yourself, and we'll talk more about this here in a second. But kind of the idea is that this tells you your valence electrons. Because before, what do we know everything about row 1? There should be 1 valence electron. Guess what? 1 valence electron. In group 2, how many valence electrons? 2. 2. You're supposed to have 3 in this one. If there's 2 in S and 1 in P, that's 3. 4, 5, 6, 7, 8. 2 in S, 6 in P, 8. Okay, so this works. These electron configurations help us see our valence electrons. Okay, so when we look then at these rings, the planetary models, this is what I meant by this only shows us electrons in the S or the P subshells. The D subshells are not shown. So in our first period, we have our S, so we have 2 electrons, and our S for helium. With neon, it has 2 in S and 8 in the outer shell, which actually corresponds to 1s2, 2s2, 2p6. And that's what you see right here for neon, whereas helium was just 1s2. What about chlorine? We already did that one, right? 1s2, 2s2, 2p6, 3s2, 3p5. How many are in the outer shell? 7. We look at the outer shell, 7. Alright? So kind of the thing to note with this planetary model is that the d electrons are not shown, but you can still see that there are 8 electrons in the outer shell is what makes it stable. And that's because your S and your P subshells want to have a sum total of 8 electrons on it in order to be stable. Alright, so concept check. Why then are there only 2 elements in the first period of the periodic table? Look back at this. Why? Is there such a thing as 1p? No, it doesn't exist. Look back at all of our charts that we've drawn. It doesn't exist. Is there such a thing as 3p? No, it doesn't exist. If you go into energy level of 3, it's too much energy. You can't contain it within a p subshell if your n is only 2. You have to jump up to 3. Oh, sorry, I meant to write, is that a 2p? Excuse me. Okay. So the number of elements in each period corresponds to the number of electrons each shell can hold. The first shell can only hold 2 electrons. That's why the first period only has 2 elements, and that's also why your first shell, your principal quantum number, only has an s subshell, because it can only hold 2 electrons in the first shell. Alright, this is kind of, I think this is helpful. The SP, D, and F designations here kind of show us where the next electrons are placed. Meaning, hydrogen has 1 electron, so it goes in the S subshell, as I've kind of designated here. So 1s1. Beryllium, 2s2. Okay, meaning 2s, and then there are 2 remaining because you already filled up 1s first. Okay, what it's doing is it's pulling the noble gas configuration. It knows it's filled, and then when you come to the next row, you start out with 2s and then you fill up that shell next. I feel like I'm not being really super clear here, so let me try this again. These designations show you where the new electron is placed, meaning 1s1 is hydrogen, 1s2 is helium. Lithium would be 1s2, 2s1. And so you can essentially use its placement on the periodic table to tell you what its electron configuration is. Meaning, I can pick any element on this periodic table and give you its electron configuration in a matter of seconds. How do I do that? So for instance, phosphorus. Okay, I'm going to come over. It's in 3. Okay, which means it ends in 3s2, 3p, because it's in the p block. And it's the third one over. Aluminum's the first one, silicon's the second one, phosphorus is the third one. So 3p3, because it's the third one over. And then you fill in everything before that. 1s2, 2s2, 2p6. And that should be the electron configuration for phosphorus. Let's check it and see if I was correct. Okay, so phosphorus, it has a total of 15 electrons. So let's make our little Aufbau diagram. So we're going to fill 1s, then 2s, then 2p, then 4s. So 1s, 2s, 2p, 3s, and then 3p, and then 4s. Okay, 15 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, and now let's write its electron configuration. 1s, 2, 2s, 2, 2p, 6, 3s. Alright, after 2p6 goes 3s2, then 3p3. Is that the same thing we said before? 3s2, 3p3. Perfect. Okay, so let's do another one. Pick one, try one on your own. How about we do xenon? Tell me what xenon's going to end in. It has 54 electrons. Take a moment and figure it out your own self. Write down its electron configuration. Alright, so let's do it. 1s2, because 1s2 filled, then 2s2, then 2p6, 3s2, 3p6, 4s2, 3d10, and notice on here starts with 3 now, and that's because it's actually a lower energy level than the 4s. It actually gets filled first. And then notice here, 4 and 5, this one is also lower. And so these guys are inserted right here. Okay, so 3d10 and then 4p6, then 5s2, then 4d10, then 5p6. Whew! Check, check, check. That's a lot, huh? And then 2, typically you actually want to represent these all in numerical order. That's the better way of writing it, so you could rearrange it in numerical order. And what that does is it places all of your 5s at the end. So notice all of our 5s are our valence electrons. So 6 plus 2 adds up to be 8, which we expect because xenon has a full shell. 8 valence electrons. Okay. Alright, so that's what we mean by orbital and electron configurations. Is the orbital ones are drawn in boxes or with lines, and you're able to see the up and down arrows which designate your different orbital spins. You're able to see the energy levels, you're able to see the subshells, and you're able to see the orbitals. Then representing it as an electron configuration, you can see the valence electrons very quickly. So for instance with silicon, you have a total of 4 valence electrons. That's what leads us to this idea of shorthand. Shorthand places the Nobel metal prior to the atom of interest in parentheses, and then it just tells us the valence electron configurations after the fact. Meaning, lithium. The Nobel metal before lithium is helium. So lithiums would be He, put lithium, put helium in brackets, and then its valence electrons goes outside of it. Okay? Or for instance phosphorus. The Nobel metal before phosphorus is neon. So neon goes in brackets, and then you write 3s2, 3p3, which is simply the electron configuration. That is so much quicker to write, and you're able to tell without a doubt that, oh, 2 plus 3 gives me 5. I have 5 valence electrons in phosphorus. Check. Okay? Now let's think about the idea of isoelectronic. This is the last big thought for this lecture today. Isoelectronic means having the same electron configuration. So think about the periodic table. How could two things have the same electron configuration? Aren't they the same element if they have the same electron configuration? No. Why not? What can exist? Ions. Because just because they have the same number of electrons does not mean they have the same number of protons or neutrons. And so two different things can be isoelectronic. Different protons and neutrons, but the same electron configuration. So let's do an example. Oxygen. What ion does it form? O2 minus. So that means it gains 2 electrons. So if oxygen has an electron configuration of He2S2 2p4, O2 minus would have to have an electron configuration of the exact same thing plus 2 electrons. So it gives a structure of 2s2 2p6. What's that the same as? Neon. Okay, so that means that O2 minus would be the same as F minus. It'd be the same as neon. It'd be the same as sodium plus. It'd be the same as magnesium 2 plus. All of these would be isoelectronic with each other. So think about it. Sulfur. What's isoelectronic with what could be isoelectronic with sulfur? Or S2 minus. Argon, chlorine minus, etc. Okay, so that's what isoelectronic means if you come across that. So to recap today, this has been a long lesson, and I hope you've stuck in there and kind of thought through all of this. Practice makes perfect on this lesson. You really can just pick any element on the periodic table and just write down its electron configuration, all the while thinking about energy, how the shells are related to each other, and how they're related within a shell. So the energy of an electron is related to its electron configuration. Electron configurations are divided into shells, subshells, and orbitals. Know the vocab. Orbital configurations depict electron spin, and electron configurations can be written in shorthand.